All right.
He was like, my mom did.
Here we go. Here we go.
The Great Bear.
You like the bear one? Okay, so yesterday, right, we put together our calculus with our polar, and we were able to do some typical things when we took the derivative, right, or using the derivative of some polar, kind of equations and stuff like that, right? Remember that the derivative with respect to x, derivative of y with respect to x, in other words, like the slope of the tangent line to a polar curve, right, is just dy d theta over dx d theta. So we take the x and y, x equals r cosine, y equals r sine of theta, and we take the derivative of those once we get them in terms of theta, take the derivative with respect to theta, and then put them in the ratio there to get the slope. Okay, so it's very much like parametric equations because we are essentially taking our polar equation, our single polar equation, rewriting it into a parametric equation. One where we have y equals stuff with theta, and one where we have x equals stuff with theta. Okay, and then we basically follow our typical parametric kind of analysis there. We can take the derivative of one with respect to theta, take the derivative of the other with respect to theta, have understanding of that. The slope of the tangent line then will just be again the dy d theta over the dx d theta, and then at particular points. Horizontal tangents and vertical tangents, right? They're just like we talked about with parametric 2. Horizontal is when the numerator is 0 but the denominator is not 0. Vertical is when the denominator is 0 but the numerator is not 0. Okay. We found some horizontal and vertical tangents, and then we found the equation of a tangent line, again, coming up with a point, an xy coordinate point, right? And then the slope, which is from the dy dx. Okay. Today, we're going to be looking at polar and integration, okay, to find the area of a polar curve, all right? The development of the polar area formula is similar to that of the rectangular coordinate system, but instead of using rectangles, right, because in the rectangular system, right, if we have like a curve, right, we would have like some rectangles that we would kind of like add up these areas here. Okay, like that. Left to right, right, because that's how we kind of like orient ourselves with rectangular coordinates. We move left, right, up, and down. So the left, right would tell us kind of like the width of our rectangles there, and then the up, down, that would be the height. The function tells us the height, right? So we would take, rectangles, and we use the area of the rectangle, which is length times width, but then we kind of do it in a calculus-y way, where we take the height of the rectangle determined by the function, multiply it by the infinitesimal width there, and we add up the integration there as a sum of an infinite number of those little rectangles, and that's how we get the area in rectangular coordinates in a certain way of thinking. Okay, but with polar, right, we're not moving left-right, we are rotating about the pole, right? We're rotating about the pole, and we're going to try and find area rotating about a center of rotation. All right? Well, instead of using rectangles then, we're going to end up using sectors of a circle, right? Rotating a certain degree amount involves using a sector, like a wedge, right, of a circle, and that's what we're going to add up is all these little wedges, all right? In geometry, you actually did learn how to find the area of a sector of a circle. It was n over 360 times pi radius squared, right? So it's essentially the area formula for the circle times whatever fraction of the circle that wedge happened to be, all right? Well, of course, we use radians in calculus for the most part, right? And so we're going to translate n over 360 to be n over 2 pi, or maybe not n, let's use theta instead for our angle there, theta. So theta over 2 pi. And then pi r squared remains unchanged because that's still kind of like, that doesn't really have to do with the angles there. Okay? And where theta then is the fraction of the circle, or the angle, and r is equal to f of theta, right? So we normally get our curve in terms of what's r equal then stuff with theta, right? And so if we take this area formula then for the sector, we'll take our area, which is theta over 2 pi, and multiply it by pi. But instead of using r, we'll use that f of theta idea, the fact that r is a function of theta squared, like that. Okay, r squared, f of theta squared. And so some things cancel here, right? So like the pi's, for example, they cancel out. Okay, and so we're left with 1/2 theta times f of theta squared. Okay. Where theta is our little, angle there, and then f of theta is our function, right, the curve described by that. Okay? Well, just like when we're talking about rectangular coordinates, where area is infinitely many rectangles, right, added together, polar area is going to be infinitely many of these very, very, narrow wedges of sectors, okay, added together as well. And so our area will be bounded, the area of a region bounded by theta equals a and theta equals b, and r equals f of theta, where f is continuous and positive, and a is less than or equal to theta less than or equal to b, okay? So the area for this is going to be found by adding up from I equals 1 to n, an infinite number of these little sector areas that we just kind of simplified the formula for there. Okay? Or that's the sum of all those little sector areas, but of course we want it to be an infinite number, so then we'll take the limit as n approaches infinity of the sum from I equals 1 to n of 1/2 these little thetas, f of theta squared. Okay, we're going to use d theta there just for like a teeny tiny, angle theta there, very small theta. All right, and so this is a familiar format that we use for integration, right? And it turns out then that the area of a region in polar coordinates will simply be the integral from theta equals a to theta equals b of 1/2 f of theta squared d theta. So it's a little bit different, right? When we talked about finding the area in rectangular coordinates, it's just the integral from a to b of the curve, right? Of just the curve, plain old curve. But that's because we were using rectangles, and rectangles was just length times width. So it's a simpler formula. It didn't require us to do anything to our curve. But now that we're finding the area in polar and we're using these sectors, right? These little wedges of a circle, we have to use that sector area formula. That formula is a little more complicated, so there's more things we have to do to our function than just the plain old function itself. We have to take our function and square it because it's pi r squared there, and then the 1/2 is also from that, that calculation there and stuff like that. Okay, so that's where that comes from. Of course, we'll use this here in just a second. All right, so let's take a look at this. So we're going to find the area enclosed by the curve r equals 2 times the sine of theta. Okay. So, it's helpful maybe to kind of think about what this is going to look like before we try and, set this up, right? Because like visually it's helpful to understand. Because right now, we know the area formula. Area formula is going to be 1/2 integral from a to b. And you can use f of theta. I'm going to write r here just for this one, but it's the same idea. R squared d theta, right? So there's our area formula, but we need to come up, well, we have an r, right? That's easy enough. We have r, it's just 2 sine theta squared d theta. We got to come up with these limits of integration, right? It doesn't tell us what to integrate over here. And so it's up to us to figure out what is the area enclosed by that 2 sine of theta there. Okay, so let's get a picture of this real quick. Let's maybe sketch this out. I'm going to try and do it maybe over in this region right here. So, okay, we'll pick some thetas and some r's here. So again, just for the sake of this one, because we're trying to figure out what this looks like, I'll start, with like the 0 there. And since we're talking about sine, I'll maybe use like the pi over 6's as well, just to help us sketch this out. So then pi over 2. And then 5 pi over 6, and then pi, and then 7 pi over 6, and then 3 pi over 2, and then 11 pi over 6. Okay. Okay. So we'll come back to this in just a second, so hold your thoughts here. We'll go over to this, though, and just take a look at this graph to see what it looks like, right? All right, so sine of 0 is 0 times 2 will still be 0. Sine of pi over 6 is 1/2 times 2 will be 1. Sine of pi over 2 is 1 times 2 will be 2. 5 pi over 6 will be 1/2 still, times 2 will be 1, and then sine of pi is 0. 7 pi over 6 is negative 1/2, so negative 1. 3 pi over 2 is negative 1, so negative 2. 11 pi over 6 is negative 1/2, so negative 1. Okay, and so then I'm going to sketch, all right, our curve here. And let's see, it looks like my farthest r that I need is 2, so I'll kind of draw like a, there's a radius of 1, and we'll say that's a radius of 2 right there, okay, to kind of help us out with that. Okay, so at theta equals 0, r is 0, so that means, you know, if we're at the polar axis here, r is 0, so we're going to be right at the pole, okay? And then pi over 6, that's like a 30-degree angle, remember, so like something along this, you know, ray right here, and then out 1 from that, so right there, we'll say. And then pi over 2, we're at 2, so now pi over 2, we're right here, okay? And then at 5 pi over 6, we're at 1, so 5 pi over 6 is this way, we're going to go 1 in that direction, so something like that. Okay. Bless you. And then at pi, we're back at 0. So if I kind of connect these here, I have to go from 0 to pi over 6 and then 0 out to 1. So it's going to curve out like that. Okay. And then from the pi over 6, I have to curve out to the 2 there. So something like that. And then from the pi over 2 to 5 pi over 6, I got to curve back in and then back in like that. Okay. So we started at 0, went out and around to there. And then, let's see here, that was, now we're at pi 0 there, so 7 pi over 6, which is like kind of this direction, we're at negative 1, and negative 1, well, if 7 pi over 6 is this way, negative 1 is going to go right back this way to this point that we found earlier, right? And then same thing with a 3 pi over 2, we're going to, you know, 3 pi over 2 is this direction, but we're going to go back to this way. And then 11 pi over 6, well, 11 pi over 6 is this direction, but we're going to go back 1 from that, so to there. So we actually end up redrawing the exact same curve. Okay, so to find the area, and the region that we create then is this curve right here. But really I should say it's kind of like, okay, you can see all those little wedges that we create, right? It's from the pole, we're kind of finding the area of these little wedges from our, for our curve there, little wedges around. All right, so what should our limits of integration be here? Just 0 to pi, exactly right, okay? If we did 0 to 2 pi, the problem would be that we kind of be counting the area twice, right? Because if we go from 0 to pi, that creates the full shape there, and then from pi to 2 pi, it kind of creates it again. So we don't need to do it twice, we really just need to cover our ground once there. So we're only going to go from 0 to pi, okay? We're only going to go there from 0 to pi, okay? It kind of like creates our shape by both starting and stopping at the pole. You can also see this if we set 0 equal to 2 sine of theta, right? So if we make our radius 0 here and we just solve, we get 0 equals the sine of theta, and then theta is, oh, my off the screen, sorry, thank you. Okay, so we set, again, r equal to 0 here to kind of create our graph. You know, it starts and stops at the pole there. We get the zeros, and then let's see here, we have theta equals, well, when does sine of theta equal 0? It's at 0, pi, and then, you know, 2 pi, and so on and so forth there. But there's your 0 and pi as well. Okay? So our limits of integration. And so now we can simplify this, right? And we can square the 2, that'll be 4, and pull that 4 out front with the 1/2 to make a 2. And then we have just sine squared of theta, d theta. Right? And now we have to integrate this. And we want to be able to integrate this by hand, right? If this was calculator active, no problem. So, how do we integrate this? Say again?
1/3 sine cubed.
1/3 sine cubed. So, yeah, the problem is here, right? If we try and integrate this, if we let, for example, we would have to use a u substitution potentially here. We could say u equals sine, then du though would be cosine, and we don't have du. We don't have that cosine there. And we can't just use the power rule then as a result of that, right? Because we can't, you know, we don't know how to integrate sine squared. We can integrate, you know, x squared or theta squared. We can't integrate sine squared like that. And so that's where we go to these identities that we need to know. So we're going to learn 2 trig identities here that will be helpful for our purposes, because oftentimes with these polar integrals, we're going to end up with both sine squared and cosine squared. So the sine squared one that's going to help us out here, sine squared of theta is equal to 1/2 minus 1/2 cosine of 2 theta. Okay. You might recognize this as like a double angle identity if you've ever used those before. Okay. I didn't teach them in my pre-calc class, but they are there. Okay. And then we'll also do cosine squared is equal to 1/2 plus 1/2 cosine of 2 theta. Okay. Let's make sure. Right. Okay, yeah. All right. So we're going to use these to help us because the nice thing that these identities that I just showed you here allow us to do, or what it does for us, is it takes something that was squared, right, and then it reduces the power to just a 1, which is helpful here. So these are identities, right? We're not doing calculus here. These are equivalent things. But it's helpful because now this sine squared of theta that we originally could not integrate, we can rewrite that as the integral from 0 to pi of 1/2 minus 1/2 cosine 2 theta. And this is something now we can integrate. Okay, so we'll break up our integral here. So we have 2 integral from 0 to pi of 1/2 d theta minus, and then 2 times the integral from 0 to pi of 1/2 cosine of 2 theta d theta. Okay, so just broke up the integral over subtraction. Yeah, Kara.
Really fast above, we had like a 1/2 and it became a 2. Did we just take like the 2 outside the sign?
So yeah, so this was 2 sine theta squared. The 2 was squared, became 4. 4 then times the 1/2 made it a 2. Do you see that okay now? Yeah, and then the sine I squared, I just left sine squared then. Yeah, okay. Thank you for asking that, yeah. So at this point, we can do a little more simplification, right? That 1/2 and the 2 can multiply, and so we're really just going to integrate from 0 to pi of 1 d theta there. Well, that's super easy. We'll be able to do that no problem. And the 1/2 and the 2 here can also multiply, and we'll end up with 0 to pi of cosine of just 2 theta d theta. Okay, what is the integral of 1 with respect to theta? Bless you. Just theta. Yeah, bless you. Just theta. Okay. Bless you again. Okay. So, and then cosine of 2 theta, right? What do we do to integrate this? We can. We need to make a u substitution. Now, how detailed you do your u substitution, or maybe some of you guys can just look at it and just integrate it without doing a u substitution, but you're going to be doing kind of like a mental u substitution in your head, right? So we need to make sure we let u equal 2 theta here. Du then will be 2 d theta. We only have a d theta. We don't have a 2 d theta here, so I'm going to move the 2 over, make it 1/2 du equals d theta. Okay? And so then this becomes, I'm running out of room here, so I'm kind of like just going to rewrite it up here. So this becomes minus the integral 1/2 cosine of u du. Okay? So again, cosine 2 theta, because we use u substitution there, if u is 2 theta, du would be 2 d theta. We don't have 2, we just have a d theta here. So make it d theta equals 1/2 du, do that substitution. Okay? Now, integral of cosine, yep, it's going to be sine, so it'll be minus then 1/2 the sine, and I'll go ahead and just resubstitute back in my u of 2 theta there. Okay? And we're going to evaluate that from 0 to pi. Okay? Which, let's see, if we plug in pi here, it'll be pi minus 2 times pi is 2 pi, sine of 2 pi is 0 times 1/2 will still be 0, so it's pi minus 0, and then minus, and then 0 and here is 0, 2 times 0 is 0, sine of 0 is 0, 0 times 1/2 will still be 0, so it's minus 0. So it's really just, final answer, pi. Way down there. Okay, pi is our final answer. Final answer. Okay, right there. All right. So, in summary, right, we started with our area formula here. All right? 1/2 integral a to b r squared d theta. All right. Our r is 2 sine theta, right? So we were able to substitute that in, no problem there. But then we had to come up with our limits of integration. The limits of integration, we were able to kind of like, figure out based on our graph here. We could see that, okay, well, if we go from 0 to pi, that alone kind of creates the graph. And then when we went beyond it, right, it kind of just continued to create the graph. So we only need to go from 0 to pi. We also saw that, we saw the 0 and pi there just from the 2 sine theta as well when we set it equal to 0 and solved, okay? And then that allows us to create the 0 and pi there. We then simplified our integral. We weren't able to take the integral of sine squared, so we had to use an identity, this one in particular, substitute in, and then we were able to integrate finally end up with pi, okay? The next one we're just going to set up, and then we'll solve with the calculator, okay? But questions on number 1 at all? Any questions on number 1? Okay. So this one, very kindly, they already gave us the graph for this. So find the area of r equals 2 plus 2 cosine theta below the polar axis as shown in the figure. So it's the shaded region right here. All right. So our integral here, right, area equals 1/2 integral from a to b of the r squared d theta. Okay. What is r in our case here? 2 plus 2 cosine theta, right? It's the curve, right? So parentheses 2 plus 2 cosine theta squared d theta. Okay. What are our limits of integration here? So pi to 2 pi, 0 to 2 pi. So what did you say? Which one? 0 to pi? 0 to 2 pi. Okay. So let's take a look here at our curve. All right. If we think about, kind of like where this curve is situated here, all right, we could imagine that at a polar axis, at the polar axis here, right, when theta is 0, the radius, it looks like, maybe starts here, okay, and then as we rotate through to pi over 2, the radius kind of, shrinks down to that, and then as we rotate from pi over 2 to pi, it looks like it shrinks down even more back into the pole. And then at pi, it extends outward here to 2 pi. Okay? So 2 pi down to 3 pi over 2 extends to there. And then from 3 pi over 2, we rotate and extends further and further out to then back to 2 pi there. So it looks like it's going to be, I think, maybe pi to 2 pi here. Okay? From pi to 2 pi. We don't necessarily need all. So Kara, do you see why it's not 0 to 2 pi here? 0 to 2 pi would also be including potentially like this upper region as well. Oh, gotcha. Yeah. Yes, if it was the entire thing, then yes, 0 to 2 pi would be right. Exactly right. Okay, very good then. All right. And then so yes, pi to 2 pi. But we have to be careful because who says that at 0 our radius extends to here? Maybe at 0 our radius is right here, and then as we rotate through we have some negative r's that then create this. Okay, and then this. So the question is, right, where, how does this graph kind of create, right? It rotates, but does it start rotating right here and go around, or does it start rotating right here and maybe go around, right? And so we don't know that. Okay, in fact, let me show you here on the calculator. The calculator can give us a little bit of a hint here. Okay, so let's take a look and just confirm that we are correct, that it starts here at 0, then goes around and ends at the 2 pi right there like that. Okay, so let's see here. I'll go to my window here, make sure I'm going from 0 to 2 pi. All right, and then I will graph it. Okay, and so did you see that? And the motion there is important. Okay, maybe I'll do it slower. Let's see, I can slow it down here. Okay, see where it starts. And then as you rotate around, you can see how the radius changes. There we're at pi over 2. And then it rotates around there. Now we're at pi. It's back at 0. And then as we rotate around, the radius starts to extend out further to then 3 pi over 2. Right, yeah, it's Mike's favorite. And then rotates back around to 2 pi. Okay, right there. So our limits of integration, for sure, are going to be what to what? Pi to 2 pi. Okay, very good. But now let me show you here an alternative. Alternative to that, right? So what if I had changed my graph here? Instead of 2 plus 2 cosine theta, oh darn, I think I have, well, I had, let me do this. Nope, okay, here. Oops. -2, graph that. Nope. Sorry, I had it. There you go. Okay. So here is a different curve, okay? But it shows up exactly the same, right? So let me just show you here real quick. Okay, so I graph both these curves simultaneously. You can see they're exact same curve, but if I go to my y equals here, their setups are different, right? The first curve is 2 plus 2 cosine theta. The second curve is -2 plus 2 cosine theta. What I'm trying to show here is that if I graph what we have right here, right, that shaded region below the polar axis, let me go back to this here. Okay, the shaded region below the polar axis. So again, that's starting at 0, rotating around. There's pi over 2 right there. And then at pi, we rotate back into the pole. And then as we extend out here, like that, back around to 3 pi over 2. And then now our radius is expanding even more as we rotate back around to the 2 pi there. So again, very clearly here, from the polar axis, it's from pi to 2 pi. But if I change my curve, okay, now watch how it's drawn. At theta equals 0, we actually start having these negative r values from then to the pi over 2. And then as you continue rotating around, now this is from pi over 2 to pi. It's these negative r values that get us down here. Then from pi to 3 pi over 2, negative r values bring us into the first quadrant. And then from 3 pi over 2 to 2 pi, the negative r values bring us into the second quadrant. So what would our limits of integration be for this curve if we're trying to find, again, this same region here? 0 to pi only, right? Okay, because it starts graphing here and then goes around to there, okay? So you got to be careful about kind of like the orientation of your graph, how it's graphed, kind of thing. Mr. Witt, how can we figure out, without a calculator, how this thing is graphing? Well, it'll be by making a little table for yourself, okay? And then you can just normally get away with just doing the quadrant angle. So like 0, pi over 2, pi, 3 pi over 2. Okay, so if I plug in 0 here, cosine of 0 is 1 times 2 is 2 plus 2 is 4. Pi over 2, cosine pi over 2 is 0 times 2 is 0, so it's just 2. Cosine pi is -1 times 2, so it'll be 0 there. And then 3 pi over 2, cosine 3 pi over 2 is 0 times 2, and so it's going to be just a 2 there. Okay, and if you like, you can do the 2 pi, but 2 pi will be the same as a 0 there. Okay, so from this, Kara, question? I mean, I think it all depends, I guess, on how your comfort level with the polar graphs. So if you can, obviously I'm writing a table out here, but you would be doing this kind of like mentally. If the more comfortable you are, you just be able to say, okay, mentally, what's happening here? As my theta is 0, I'm going to be at 4. So okay, that's where I'm starting. At 0, it's 4, and then as I rotate around, well, then obviously I'm going to have to go this way and then this way, kind of thing. So, that could be helpful, maybe. Does that make sense to you about what I'm saying there? So. Essentially, yeah, once you kind of get the radius equal to 0, you know your starting point, and then maybe you pick one more point, just to help you convince you that you're going in the correct direction, right? We're not going down this way, we're going to go up this way kind of thing. But once you get that, then you're pretty good to go, right? You're going to okay, well then I'm going to go around here and then around here like that. So really you only need 2 points, I would say, in this case, right? But you can see, okay, there's our 0, 4, there's our pi over 2, 2, there's our pi 0, and then from that pi then, there we create the 3 pi over 2 and the 2 pi, there's the region right there. So it's from the pole, which starts at pi, out to then the polar axis there at 2 pi. Okay, so yeah, question.
What was the other equation that was the same graph?
It was -2 plus 2 cosine theta. So yeah, I'll say, so compare to r equals -2 plus 2 cosine theta there. They're exactly the same shape, but they're created in a different manner, and so that really result in different, and I'll go ahead and put the integral for that one. It'll be from 0 to pi, as Lander said there. Okay, so again, we're not going to do this one by hand, okay? You could do this one by hand, potentially here, what you would do is you have to FOIL out the 2 plus 2 cosine theta. Okay, so it would be 2 plus 2 cosine theta times another 2 plus 2 cosine theta. And then you would like, well, I'll just write it out here real quick. It would be like 4 plus 8 cosine theta plus 4 cosine squared theta d theta. Okay, this you can integrate no problem, right? This one you would have to use the 1/2 plus 1/2 cosine 2 theta to do. Okay. So you could do this by hand if you wanted to. We're just going to try and save some time because I'm already going really long and everyone's starting to fall asleep. So, oh, good. All right, so Math 9. Hopefully that just means you guys understand this so well and you're feeling good about it. Hopefully. All right, so I'm going to use, I'm going to use actually the function mode here, but you could use polar mode if you want to. I'm just going to do it in my calculator. And I don't forget to put the 0.5 in front, like that. Okay, so there is 0.5 pi to 2 pi, 2 plus 2 cosine x in my case, quantity squared. All right, and then with respect to x, so we hit enter, and we get about 9.424777961. Okay, so there's our answer, the area of that half of the graph. Okay. Now, the other thing that we're going to want to utilize in polar especially is symmetry, because polar graphs tend to be symmetrical. Okay, not always, but they tend to be that way. With that being said, then, let's say that we wanted to do what Kara was originally, talking about here. Let's say we wanted to find the area of the whole graph. Would we need to set up an entirely different integral here and then find that value? Like, will we need to set up an entirely new integral and then integrate that and get our answer here? What could we do with this? Multiply by 2. Yeah, just double it, right? This bottom half is exactly a half of the whole curve there. So we could just double this and get the area of the whole thing. So please feel free to also take advantage of that symmetry too, if you'd like to, right? Maybe it's easier for you to just find the area of half of it and then double your answer. Okay? All right, any questions on example 2? Okay. Let's take a look at example 3. So let R be the region in the first quadrant. This is this region right here. That is bounded by, now if you guys just look at that right off, kind of without, first glance there, I'll say, first glance. That looks like something we did way back. We talk about area of a region between two curves and stuff like that, right? This looks like a line and maybe like a quadratic or something like that, and it's just like find the area of the region between these two curves using rectangular coordinates. But in fact, this is a polar region and a polar curve, okay? The polar curves are r equals theta and theta equals k, okay, where k is a constant and 0 is less than k is less than pi over 2. Okay, so take like 30 seconds here, maybe a minute, all right, and just identify which one of these curves is the r equals theta curve and which one of these curves is the theta equals k curve. Okay, which one is which? Which one is which? Okay, and you can identify, you can distinguish between the two. So think about that. Okay, which one of these two curves here is r equals theta? Which one of these is theta equals k? I'll come back in like a few seconds here, and I'll give you a little hint maybe to think about, and then we'll continue on. So think about which one of those two curves is theta equal to, is r equal to theta, and which one is the other way. Okay. So r equals theta means that the radius of our curve, the radius, how far it is from the pole, is going to be changing as theta changes, right? Exactly the same rate. So that means if theta is increasing as you're rotating more and more and more, your radius should be then also increasing as you rotate out, right? As you rotate around, okay, counterclockwise. Okay. So which curve then is r equals theta if that's the case? It's the curvy one. It's the bottom one. Exactly right. Okay. This curve right here is the r equals theta curve. Okay. Which then makes, by process of elimination, right? That makes this theta equals k. Okay. Now remember, k here is a constant, so it's just going to be like a single number. Why does this theta equal k produce this straight line here? Because that's like the theta, the angle theta there, right? For this entire line creates this, every theta for this, any point on this line, the theta is going to be the same because it's the same angle off the curve, okay? It creates that straight line there. Remember, it doesn't, like, theta equals k has no bearing on what the radius or the r value would be here, so it's just going to be, any distance from the pole, but in that direction theta, okay? So those are the two polar curves here. K and R the same thing. K and R would be the same thing here and here. Do you see what I'm saying? Does that answer your question? Yeah. It would be the same thing here and here. Okay? So, with that being said, we're going to find the area of this region. So let's set it up. So we'll say A equals 1/2 the integral from A to B of our radius squared with respect to theta. Okay. And again, we're trying to find the radius, the area of this region, so we're going to create like these little wedges right here. Or I guess it's going to really curve around like that. Okay, they all kind of come in from the thing there. So what curve here is determining our radius? The r equals theta. Exactly right. R equals theta is determining our radius here. Okay, so R is just theta in this case, right? It's just theta. We will be talking later about how to find the area of a region between two curves. All right, but right now it's just going to be theta squared d theta. Okay, what are our limits of integration going to be? 0, right? Because we have to start at the angle 0 here, where, 0, 0. And then we're going to rotate up around through here to this value, which is a theta equals k, right? So then k is our upper angle there. Again, we're rotating here about the pole. So from 0, we rotate outward up to that theta equals k, right? That's an angle of theta equals k right there. So there's our setup. Okay? But we're going to continue and actually find the area of r in terms of k. So we're actually going to integrate this, right? So what's the integral of theta squared? It's gonna be 1/3 theta cubed, right? So we'll have 1/2 though, so make it 1/6 then theta cubed, right? It's just the power rule. That's all there is to it. Integral from 0 to k. Okay, and we'll plug in the k. So it's 1/6 k cubed minus 0, so it's really just 1/6 k cubed equals the area of r. Like that. Okay. Questions on any of that? Carrie, yes. Okay, so like the setup you're saying?
Yeah, like when we were identifying which one was on the
Oh, which curve was which curve was which? You're saying? Okay, so again, the two angles here, or the two curves here, r equals theta. So what that means is, right, r directly depends on what theta is. So theta equals 0, r is 0. So that's the point there. But of course, both the straight line and the curvy thing both have a point at 0, 0. It looks like, right? But as theta increases, that means as we rotate from 0, outward here towards the pi over 2, what's going to happen to r? R is going to increase simultaneously to that, and so the r is going to extend, starting at 0, it's going to extend further and further and further and further and further out from the pole as we rotate around. Whereas compare that to theta equals k, okay? Imagine graphing this. Theta equals k has no bearing. Like r doesn't change. I mean, no matter what r is, the theta will always be whatever k is, and so that angle doesn't ever change. R can change, but the angle won't change, and so that's this right here, right? The angle is not changing at all, but the r can. That's okay there. Does that make more sense now? Okay. Yes, Gabe.
I
1 over theta. That's supposed to be 1 over 6. Yeah, sorry, that's my sloppy handwriting there. It looks better the next line, but yeah, you're right. It's supposed to be 1 over 6 now. Okay. So yeah. Other questions? Okay. So let's try number 4 then. Let's keep going here. All right, now this one, no calculator allowed for this one, so we're going to be on our own here for this. The graph of the polar curve, r equals 1 minus 2 cosine theta for 0 less than or equal to theta less than or equal to pi is shown above. Let S be the shaded region in the third quadrant, bounded by the be the shaded region in the third quadrant, bounded by the curve and the x-axis there. Okay, so we're in the third quadrant, and that's this. It's not really shaded, but you know you can kind of get the idea there. Okay, that guy right there, that little shaded area in the third quadrant, S. Okay. So letter A asks us to write an integral expression for the area of S. All right, no problem. We've been doing that this whole time. So area equals, well, actually, why don't you guys go ahead and give this one a try? Okay, we just did a couple of these. Give it a shot. Okay. I'll give you the setup, right? 1/2 integral from A to B of r squared d theta. Doesn't say to solve it. It just says write the integral expression. So all you got to do is just set it up. All right, so go ahead and see what you can come up with there. Set it up. Okay, and I'll kind of walk around and see if you've got questions or something like that. I'll need to do my answer first, though. Okay, so your two main tasks here: find your limits of integration, and also figure out what your curve is there, right? Not this sheet, which we'll find there, this region right there. Yeah, in the third one, the region of the third quadrant. Think about it, okay? Okay, so, but again, it's not this region, it's this region right here. Yes, the third one. Third one, yes. Okay, looking good. Okay, close. How did you get this? Yes, you want to, so you're close, you're the right idea. You want to, when does that equal 0? Why do I want to hit the whole? But it's not pi 4. Pi 4, remember, cosine of pi 4 is root 2 over 2. So, yeah. Yep. So if you start, what's helpful here is let's figure out just where we're starting. So if I may chop by here, all right, theta and r here. Let's just start with theta equals 0. By plug 0, it's starting with 0, right? Cosine of 0 is 1 times 2 is negative 2. And 1 minus that 2 is negative 1. So 0, negative 1, this is our starting point. Even though angle is 0, it's a negative r value, so it's 0 when we go back from that.
You're doing this whole thing right here.
Right? So far so good?
Okay, but it's
Then let's just go to the next easy one, which would be pi over 2.
So what you're gonna do?
Okay? At pi over 2, we're starting at this angle right here.
Goes like
Pi over
this.
cosine of pi over 2 is 0, times 2 is 0, 1 minus 0 is 1. So it's pi over 2, we're at 0. So that means we're going from here around to here. Right? So, oops, sorry. We're going from here around up to here. So we're going around here, through here, and that point we just found pi over 2 is at 1. So you got to figure out what this, exactly you want to include. It would be from 0, because remember this point it starts from 0. I'm going to go from 0 around. You got to figure out what this point is. It's between 0 and pi over 2. Like 0 gets us to here, pi over 2 gets us to here. So you got to figure out what point there between the what's between there is pi over 6. Cosine of pi, or sorry, not cosine, pi over 6. Sorry, pi over 3 is the
Messy, Mr. Lemire.
Yeah, that's me. Cosine of pi over 3 is 1/2 times 2 is
Dude,
1.
it's practice.
1 minus 1 will give you the 0. So the pi over 3 is just me.
Me and Joe versus you.
Yeah, you just want that bottom region right here. Just this.
So it's 0 to pi over 6.
Yes.
Dude, Zach
Pi over
is
3,
so,
pi over 3.
like, done to try to,
Oh,
like,
yeah,
drop
pi
the
over
squat on.
Okay. So there is your answer. Okay. If you got the R, good. Okay, but it's really important, right, that we get the correct limits of integration. 0 to pi over 3. Okay. Any questions about how to come up with those limits of integration?
Yeah.
Yes. All right. So let's talk about that table again, right? So we'll start at 0 because that's where our curve starts, is at theta equals 0. At theta equals 0, the radius r, right, cosine of 0 is 1 times 2 is 2, but 1 minus 2 gives us a -1. So 0, -1, we start right here, which is weird because that's this way, we think that's like theta equals pi, but because when we put in theta equals 0 this direction, we get a -r value that brings us back to here. Okay, so theta equals 0 brings us back 1 to there. All right. Then I'm going to throw in another point here. Let's use pi over 2, for example, like the next, kind of quadrant angle here. At pi over 2, cosine of pi over 2 is 0 times 2 is 0, and then 1 minus 0 is 1. So then at pi over 2, we go to positive 1, this point right here. So here's theta equals 0, here's theta equals pi over 2. So we're rotating from a -r value to a positive 1r value. That means we have to go through what r value? From -1 to 1, we have to go through what? 0 by the intermediate value theorem, right? We have to hit all the numbers in between the -1 and 1, right? Because cosine is a continuous function. And so we go through 0, this pole right here, right? We go through 0 somewhere between 0 and pi over 2. Well, if it's non-calculator, we don't have many options for angles theta that go between 0 and pi over 2, right? We have pi over 6, we have pi over 4, and we have pi over 3. Well, if we do pi over 3, cosine of pi over 3, 1/2 times 2, 1. 1 minus 1, 0. So at pi over 3, right, so somewhere in this direction, we're actually at the pole right there. And so it's from 0 to then theta equals pi over 3 is at the pole right there. Okay? So there's our setup. All right, but thankfully, all we have to do is set it up. All right, letter B. Go ahead, do it. Write an expression for dx d theta and dy d theta in terms of theta. Okay, so this one you actually have to find. Remember, right, that x equals r times the cosine of theta, and we know what r is. What is r in our problem? 1 minus 2 cosine theta, and then times the cosine theta there, and so you can take the derivative of that with respect to theta, right, and you can do something very similar with y. R times the sine of theta. Okay. So thankfully, this is a bit of a break from the graphing stuff that we were just doing there. So anyway, go ahead, do that, and again, find dx d theta, dy d theta. I messed up here. This should be sine theta there. I fixed it now. Yep. And that should be. Oh, thank you. It's actually a little cough that I do, but I'll take the blessing anyway. You ever seen Zoolander when you have the black lung?
What?
You guys ever seen the movie Zoolander before?
No.
Yeah, I've seen it.
Anyone? Where he was working in the mine or whatever. He's like,
He's like, I've got the black
yeah,
lung,
exactly.
Bob."
Yeah, exactly. Yeah.
And then he shows up on the TV as a mermaid.
Merman. Yeah, exactly. Yes, exactly. I did not like that movie when it first came out, but upon repeating watchings, I liked it more and more. So.
How many times have you seen it?
Maybe like I don't know. It's on TV a lot. I feel like too, like on FX or something like that. Zoolander. I don't know. Maybe like 5 or less. I would say. So, but I saw it in theaters. It was like, oh, whatever. But then I saw it later because I was like, oh, this is not that great. And people were like, no, it's a great movie. You need to watch it again. And I did. I was like, oh, all right, it's better now, I guess.
So you're a follower.
Now I am. Yes. Now I am. Anywho, all right. So if you're still working on B, keep working, or I'm going to post the answer for B. If you feel like you've got B good, or you check yours versus mine or whatever, and you think you've got it, then move on to C, okay? So again, if you haven't finished B yet, don't look up because you're going to get spoiled, right? But no spoilers, right? But there it is. All right, and then if you want to, if you like check B and you're like, yeah, I got it, then move on to letter C, because once you've got B, then really you should be able to do C without too much trouble. Remember for C, though, you're finding the equation of a tangent line in terms of x and y. So it means you need to find an x coordinate and a y coordinate, right, for your points and stuff. So oh, yeah. Camera question? Right back. Because when you multiply by the derivative of cosine is negative sine. And so then the negative, when you do the chain rule here, it'll be 4 cosine theta. It will be minus, but then times the derivative of what's inside, which is the negative sine theta, so it makes it plus 4 cosine. Yeah, question?
Is there any way you can simplify the dy d theta with trig identities?
Kind of. Like, for example, a Pythagorean identity here, you won't be able to use sine squared plus cosine squared because there's no way to, like, even if you factor negative 1 out, it won't work. What you could do is at least, like, get everything in terms of cosine. You could rewrite, the sine squared as 1 minus cosine squared, distribute the 2, and then you have some, like terms to combine, but it'll be similar. It'll still have 3 terms in it because you're going to have like a cosine term, a number, a constant, and then a cosine squared term. So it's kind of like debatable about whether it's more simple than that or not. But so yeah, sadly, because one sine squared is because the sine squared is positive and the cosine squared is negative, you can't make them cancel nicely, unfortunately.
I like your positivity, Mario.
I Scooby-Dooby-Doo hate this. Do I need this in my life?
Yeah.
Do I?
Is it?
I know what y equals 2.
Dude, Megan, I totally was seeing Megan.
Okay, I'll go ahead and post. So there are your solutions for A, B, and C. Again, if you're still working, please do. I'd like to at least start on number 5.
No.
Yes.
I feel like you did last time. Just basically.
I would like to at least start on number 5. Okay. So, yes, question.
Voice in the video.
Yeah. Yes, you could have. Yes. Pi r squared, right? So the radius of that is 1. Yes. Yes. It's a lot of calculus for a simple geometry problem.
Remember we had a sub Mr. Golf this week, just watched this video. Anyway, I'm sounding my voice and Hi everyone, in Mr. Golf's class.
They don't always watch it unless they need to. He's going to be there today, so.
Let me know when
I
you
used to
sit.
watch it.
Okay. I'll be sure to do that. Mikey had a sub yesterday. Sorry, you forgot.
How come Mr.
Wait,
Goff
did he?
has subs and we can't have subs?
Good.
Oh, no.
Yeah, good
Mr.
set.
Goff had like a sub. Oh, because Mr. Goff went to Antarctica. I don't do cool things like that.
He just goes to Antarctica?
Yeah.
Wait, you went over Christmas break.
Yeah.
For like a week,
he planned this from like.
for a week straight, we were just
Okay.
listening to Meyer talk.
I just kind of
Yeah.
thought that he was just like.
And
a
now
month
Mike gets
before,
for a
it's just
whole
like, yeah, I wanna go to Antarctica.
semester.
No, he did it for his
That's nice.
Yes. It was like a bucket list kind of thing. He
I
wanted
remember
to.
hearing kids
I imagine it was really
Check
warm.
on
ask questions in class.
It was.
I was like,
warmer
There's summer there. Yes. It was warmer there than it was here.
In the snow and slept in on this, and like
Yeah.
Arca things.
It's their summer too, so like the sun was up, you know, most of the time.
It was like it was.
So yes.
Why did you solve it at dy over dt?
So there's no difference.
Because I wrote it down incorrectly. It should be dy dx. Thank you. Sorry. Yeah, sorry. It should be dy dx there. Of course, that is in terms of theta. So yeah. So yeah. Yep. Thank you for pointing that out, though. Yes, that is important. Thank you. Sorry, that is dy dx. Check this. Make sure I have it written correctly there. All right. So I'd like to try and at least get started. I do have dy dx written there. I just wrote it incorrectly. Okay. So I'd like to try and get started here on this next one. So let's move on. Any other questions on? Any other questions on number 4? So by the way, number 4. That is a free response question from an actual like AP test. It's a Form B, 2009. Okay, but I mean like that's like that's kind of the expectation, right? That wasn't too terrible.
Before the AP test, are we given like what do we do to prepare?
What do you do to prepare?
Like to go back and do everything from AB and to.
What we'll do. So the review is going to run essentially like we're going to do as soon as we finish the new stuff, right? The very next day we will jump right into taking a practice AP test. And the purpose of that is not to screw you guys over because it's gonna but the purpose is to give you like a baseline. This is where you are right now. If you don't do any studying or anything like that, that's what you can expect to how you can expect to do. Counts as a test grade. Hang on, it gets curved and stuff like that. Gets curved. Then as we go throughout the class, we'll be focusing mostly on reviewing multiple choice in class, and then for homework, we'll be assigning past free response questions. Maybe like 1 or 2 a night kind of thing. And then as we progress through that, I won't play like review games and stuff like that. It won't always be just like multiple choice. That'll all be term 4 stuff, yeah. And then at the end of review, prior to the test, we'll take another practice test to kind of hopefully see some improvement, right? And like you guys get some last minute studying, and you can see again because we don't just focus on like the big picture. We also focus on if you have specific topics that you struggle with, so you can focus on those kind of thing. Simultaneously to that, right, on a Saturday there is like a practice test, another test that we give you that you can then the enticement there is you can replace your original test grade with that second test grade on the Saturday test. So that to help people, kind of like help their grade if they really want to, or people that feel fine about that first grade, they don't need to come in for the Saturday one, kind of thing. All right, and then that should cover pretty much all the review then. Yes, Gabe.
How many more units of this do
We
we have?
have I think at least one more, but I think the next unit gets split up into 2. So after this one, I think there's 2 more, but it's like normally one unit gets split into 2. All right. We'll hold off here then. I don't want to now jump in. All right. Any other questions for me about this stuff though? All right. The next one's not too terrible. It's a similar thing. It's just we're trying to find the area of the inner loop, but it's just a matter of figuring out what the theta values are there. But I'm not going to worry about that for right now. We'll do it tomorrow. Okay? So, your class, on the classroom, of course, homework will be posted. Don't forget to get started on that new problem set as well.